The last thing we're going to look at is everything we've looked at so far has been all in one dimension. We've assumed the particle is in a box that's along a line. But there are other interesting problems and applications that involve a particle being trapped inside of, say, a cube, a three-dimensional object, or a two-dimensional object, a particle on a sheet, a particle in a cube. Sometimes electrons inside of nanoparticles are modeled as a particle inside of a sphere. And so it's useful to know, how do we deal with this in 3 dimensions instead of just 1 dimension, right? We started with the easy one. Now we're going to up the ante a little bit and go to 3 dimensions. So we'll consider a case where the particle is now trapped inside of a 3-dimensional box. So if we kind of want to draw this representation here, we'll see how I can do with this. So our particle is trapped inside this box. V is infinite outside of the box, and again, V is 0 inside of the box. Now, to be able to solve this problem, we need a 3-dimensional derivative, right? So our Hamiltonian operator in 1 dimension is negative h bar squared over 2m times the second derivative with respect to x. We need an equivalent for this for 3 dimensions. And so this is what's known as the del squared operator. This is a 3-dimensional second derivative. And del squared is equal to the second derivative with respect to x plus the second derivative with respect to y plus the second derivative with respect to z. And this is a 3-dimensional derivative. And so we can now rewrite our Schrödinger equation with our second derivative as negative h bar squared over 2m times del squared psi is equal to E psi. Right, so we have essentially our same setup, but now we have a 3-dimensional second derivative instead of a 1-dimensional second derivative. Okay, our boundary conditions for this problem are similar to before. They are at the edges of the box, of our cube, I should say. We have that the wave function has to be 0. So when x is equal to 0, now this is a whole line now, it's not just one point, but it's a whole line. When x is equal to 0 and when x is equal to a, psi has to be equal to 0. And one thing I forgot to mention is that we'll call the lengths of the box, so the x dimension length of a, y, the height of the box, will be b, and z, the depth of the box, will be given by c. So we have these, I say it as a cube where a, b, and c are the same. They could be different lengths, right? This could be a rectangular prism instead. And so for the y and z variables, we'll have a similar set of boundary conditions here. Right, when we're at the edges of the box, our wave function has to be 0. Okay, so we have very similar setup to before, but now we're dealing with x's, y's, and z's, not just one of them. Now, when we have an equation with multiple variables, and we're looking at a differential equation, let's separate the variables. And so we'll tackle this as a problem where we have our wave function is going to be some function of x, y, and z, but we'll say it has an x part, a y part, and a z part that we can all treat independently. All right, and so we'll pick up from here in the next video.